Okay, in this video we're going to start taking a look at section 15.6, which is triple integrals. So that's going to be things like this. I'm going to have E is a finite solid. So that's going to be a three-dimensional region. It's got to be finite, so it doesn't go off to infinity in any directions. It does have a fixed volume. Okay. And I'm going to be taking a look at the triple integral over E of f of xyz dv. And you could probably guess that that v stands for volume, because if we were to set this up, we would go through our usual four-step process. We would chop E up into little rectangular boxes, and each box would have some volume, delta v. That would just be delta x times delta y times delta z. Okay. And we would approximate, we would add, we would take the limit, we would get a triple integral. Okay, I think we've done that often enough that I don't need to write that out again here. I will just point out that if you do that, you get a triple Riemann sum. Okay. All right, so if we have this, the question is, how do we evaluate this? And it's going to be very similar to what we do for double integrals. We're going to evaluate this as an iterated integral. We're just going to have to integrate 1, 2, 3 times. So we're going to want to move to having specific limits of integration, and instead of dv, dz, dy, and dx. Okay. All right. So, I'm fine. Don't worry. All right. The interesting cases are going to be when E is not just a rectangular box. Because if E is just a rectangular box, we've got constant limits of integration for everything. The interesting situations are going to be when E is either type 1 or type 2 or type 3. Now this is a type 1 region in 3 space, which is different from a type 1 region, of course, in 2 space. Okay. I'm just going to talk specifically about a type 1 region, and then just mention that it generalizes to type 1 and type 2. Your book doesn't use this vocabulary, but I kind of like it. Other textbooks call this type of region a simple XY solid. Okay. And so here's the basic idea. D is going to be the projection of E onto the XY plane. Now, what do I mean by that? Well, let's just take a look at an example. Let's suppose E was the solid unit sphere. When I project a solid like that onto the XY plane, I'm just going to take every single point in this sphere, and I'm going to drop a perpendicular. Now, sometimes I'm dropping down, and sometimes I'm dropping up, okay? But I'm going to drop a perpendicular onto the XY plane. The set of all points on the XY plane that get hit when I drop these perpendiculars, that's my projection. And I can see that for the sphere, that would just be the solid unit disk. So this becomes the common domain then for what I like to call the floor and the ceiling. So those would be the surfaces that bound my finite solid. In this case, the floor would be the lower hemisphere. The ceiling would be the upper hemisphere. Okay. Now, if this is going to be a type 1 region or a simple XY solid, we are going to put a restriction on D. It must be type 1 or 2. Now, of course, since D is in 2 space, I'm talking about type 1 and type 2 regions in 2 space. Remember, that just means that you can bound it with 4 functions, 2 constant functions and 2 continuous functions, either constants on the left and right and continuous functions on the top and bottom, or those roles reversed. Okay, and I know that the unit disk is both a type 1 and a type 2 region, so we would be good to go. Then I'm going to have U1 of xy and u2 of xy, and these would be continuous functions defining that floor and ceiling. So basically defining the bottom boundary surface and the top boundary surface. Okay, so, and U1 I'm going to say is the bottom one, U2 is the top one. Okay, so if this is the unit sphere, I know that's x squared plus y squared plus z squared equals 1. I can solve for z. Z squared is 1 minus x squared minus y squared, so z is plus or minus the square root of 1 minus x squared minus y squared. Okay, so the negative square root would be my U1. That's what's describing the bottom surface. The positive square root would be the U2. That's what's describing the top surface. Okay, so if we were to set up a triple integral over this sphere. So here we're saying that this is our E, is the solid unit sphere, which means that D, the projection, is the unit disk in the xy plane. So if I were to set up a triple integral over E of f of x, y, z dv, I'm going to do it as an iterated integral. But I'm going to do this in a couple of steps. First of all, I'm going to break it up into a double integral over d, and then a single integral from the bottom to the top. Okay. Of f of x, y, z, and that would be dz dA. So dz for this integral, dA for this double integral. Now with our particular example, that would be the double integral from d, the integral from negative root 1 minus x squared minus y squared to positive root 1 minus x squared minus y squared, f of x, y, z, dz dA. Now, I can then go to expressing this as an iterated integral. And I know I can do that. I'm going to just set it up in rectangular coordinates, but don't worry, we'll come back and chat. Okay. All right. So if d is the unit disk, that's just x squared plus y squared equals 1. If I were to slice it this way, then I can see the slices are going to go from negative 1 to 1. That would be my dx. Along each slice, here y is plus or minus root 1 minus x squared. So along each slice, I'd be going from negative root 1 minus x squared to positive root 1 minus x squared. That's my dy. And then I've got my integral from negative root 1 minus x squared minus y squared to positive root 1 minus x squared minus y squared, f of x, y, z, dz. Okay. Couple of things to point out. First of all, when I integrate with respect to z first, these limits of integration are allowed to be functions of x and y. I can have two variables here. I can have a function of one variable here. I must have numbers here. Okay. Now, that's because when I take my antiderivative with respect to z, I'm going to plug in this for all my z values. Then the z's are gone, I've just got x's and y's. So then I take an antiderivative with respect to y, I plug in these functions for y, the y's are gone, I just have x values. Then I take an antiderivative with respect to x, I plug in these numbers, I have a number. Okay. So it must be that each time you integrate, you're eliminating a variable. Now, if the variable didn't exist, wasn't in the problem to begin with, that's okay. If there were no z's here, then I wouldn't really be getting rid of the z's, but I would be getting down to a problem that just had x's and y's, and then just x's. Now, this is written as an iterated triple integral. Here I've broken it down into a single integral followed by a double integral. There's some advantage to doing that, because you may have noticed that we were working on the unit disk here, and you might have said, but I don't want to do the unit disk in rectangular coordinates, I'd rather switch to polar. And you absolutely can. Okay. So when you get to this double integral, you can do that in either rectangular or polar coordinates if you want to. And in fact, 15.7 is going to be taking a look at something called cylindrical coordinates, which is basically going to be using polar coordinates for the xy plane and then attaching a z value. So that would be like switching to polar before you even set anything up. Okay. All right. One last thing here. With this particular example, we didn't have any walls. We didn't have any walls because the floor and the ceiling met. Okay. Sometimes, though, you're going to have a region that does have walls. So I could have E is the region inside the cylinder, x squared plus y squared equals 25, between z equals x squared plus y squared and z equals -2. Okay. Now, these two curves are never going to meet, so the floor and the ceiling don't meet. That's okay, I've got some walls. We're working inside of this cylinder. And then I've got these two surfaces. Let's just say down here, this is z equals -2. That's my floor. I'm going to have some paraboloid up here. I'd be looking at this region in here, between that plane and that paraboloid. The projection onto the xy plane is just going to be the disk of radius 5. Okay. So there I had walls connecting the floor and the ceiling. So sometimes the floor and the ceiling meet, there's no need for a wall. Other times you need to be given a wall. So I want to recognize this didn't have any z's in it. That's just describing the side boundaries. Those are the walls. These are my top and bottom functions. So here I would set this up as a double integral over d of the integral from -2 to x squared plus y squared, f of x, y, z, dz, dA. And then I could decide I would probably choose to describe d in polar coordinates and switch when I got to that double integral. Okay, so that's just some of the theory about setting things up. In the next video, we'll actually do an example.